Circuits with combinations of inductors and capacitors can exhibit oscillatory behavior, and this behavior manifests itself in currents that rapidly change direction. In this particular problem, we'll be looking at a simple circuit with one inductor and one capacitor. So have a look at the problem statement. So this kind of problem is actually somewhat realistic in that we're given a voltage and we're given currents, and these kind of quantities can be read off of oscilloscopes or multimeters. And using knowledge of those, we could find the other circuit quantities, or we could verify what the inductance is. We could also find the oscillation frequency. So this kind of experiment could actually be carried out in a lab setting. To begin this problem, we'll note that essentially what we're going to do is start out by using Kirchhoff's loop rule. And then using that loop rule, we're going to find a differential equation which you have to solve for one of the quantities as a function of time. So to begin with, let me go ahead and write down, just draw a picture of the circuit that we have here. We have a capacitor in series with an inductor. And if I just use Kirchhoff's loop rule for this, the voltage across any capacitor is the charge divided by the capacitance. And then the voltage across the inductor is the inductance times the rate of change of the current with respect to time. So the loop rule says if I start at a single point and then go around, I have to add up all the voltage changes across each circuit element. So starting here, the first thing across is a capacitor. I drop Q over C voltage. And then across this guy, I drop L times di dt voltage. And then I'm back to where I started, so those have to add up to 0. That's the statement of Kirchhoff's loop rule. And we want to solve this. This is a differential equation because we have some derivatives here. The problem is that we have two different quantities that depend on time. We have both charge and current. And so solving it is not trivial because we have more than one quantity here that we have to solve for. However, they are related. We can use the fact that current actually is the derivative of charge with respect to time. So this is just saying that the current, which is in which is in amps, equals the rate of change of coulombs per time. That's a definition of current. And we can use that to get rid of the current in this equation. So if I plug this I into here, what I'll essentially be doing is taking another derivative of this quantity, so I get the second derivative of charge with respect to time. So rewriting that equation, we'll find the following. I'm taking two derivatives of Q, so it'll be this guy. And I still have the L there. Okay. So that's a differential equation. Now I've got it in terms of a single variable with respect to time. And let me just rewrite it as the following. I'll write it as... So I'll move that term on that side and then divide the whole thing by L. All right, now you could solve this systematically using the theory of differential equations, but it's a pretty straightforward equation. And if you just kind of think about it and inspect it for a while, you may realize how to get the answer. So this is essentially saying that we have a function whose second derivative equals a negative of the function itself. What type of function would satisfy that? Maybe sines and cosines, because when you take the derivative twice, you get back to themselves, and there's a minus sign there. So the solution to this, one solution, is a cosine of some constant times time. And if you take this derivative twice and then plug it into this equation, you'll find out that to make this equation work, you have to have omega equals 1 over square root of LC. Right, so this is one solution to this problem. You could also use sines, or you could use a combination of sines and cosines. Which one you use depends on the initial conditions, which are not given here, so we don't have to worry about that. I'm just going to choose cosine arbitrarily, but if you use sines, you'll still get the right answer ultimately. One other thing I want to say is that this constant here also depends on initial conditions, but it's related to something we're given in the problem. We're given max voltages, and this Q0 is actually the max charge. And the reason that's the case is because cosine oscillates between 1 and negative 1. And so this quantity, the biggest it can get is 1 times whatever the coefficient is. So this Q0 is actually the max charge held on the capacitor. And when this quantity is 0, this charge actually is at its max, but when it's something else, it may reach to something lower. And then if it's a little further, you may get something that's negative. So this is essentially oscillating between positive Qmax and minus Qmax. What we're given here, though, is the voltage. So what I'm going to do is rewrite this in terms of voltage to get that quantity in here because we know what it is. So just using this equation, I can just plug that in here. Q equals V times C, so this is going to be V max times C. Okay, so this tells us that the charge on the capacitor plates equals the maximum voltage that it can hold times its capacitance times this oscillating factor. And now from here what we can do is we can actually write an expression for current. And then using that expression we can maybe kind of find out one of these quantities because we do know the max current in the circuit. So once you do that on your own, and that is using this expression, find an expression for the current as a function of time, and then use what you know about the problem to try to find omega. Try to find the oscillation frequency. Take a minute and do that now. So to find the current from the charge, again, you take the derivative with respect to time. So differentiating this quantity with respect to time, we get the following quantity. We get the current equals, we get the coefficients out front, which don't change. Using the chain rule on the cosine, we're going to bring out an omega. And then the derivative of cosine is sine. And there's a negative out front because you're taking the derivative of cosine, which makes this a negative sign. Now, what we're given here is a max current traveling through the inductor. And we know that the current at any given time is given by this quantity. And using the same reasoning as above, the coefficient of this quantity will be the max current because this quantity can only oscillate between 1 and negative 1. So whenever this quantity is, in this case, negative 1, the current will be maximized based on whatever the coefficient is. So again, the coefficient here, the absolute value of the coefficient, which is these three factors multiplied, is the max current you can have through the inductor because this can only be as big as 1. So the max current is the product of the max voltage, the capacitance, and the oscillation frequency. And we know that this has to equal 50 milliamps as given in this problem statement. All right, and we know that the Vmax is 1.5 volts. We know the capacitance is 4 microfarads. So solving this for omega, you'll find that omega equals about 8,333 radians per second. And this is, again, this isn't radians per second because it's an angular frequency. If you want to find the frequency in hertz, in other words, cycles per second, so how many times it switches direction each second, just divide this guy by 2 pi. Now that we have that, the other part of the problem is asking for what is the inductance value. And that's a pretty straightforward calculation, so go ahead and carry that out on your own using what we know from up here or over here. Take a minute and do that now. So when we solved the differential equation, we found that the angular frequency had to equal this quantity. And we're looking for L here, so if we just invert this quantity, we'll find, using this value, you'll find that 8,333 must equal 1 over the square root of L times the capacitance, which is given right there. So if you solve that for L, you're going to get that the inductance must equal 3.6 millihenries. And so that's the answer to the problem. Short and sweet. Let's take a look at the summary. In this problem, we were asked to find unknowns in an LC circuit. First, we used Kirchhoff's loop rule to get a differential equation for the charge on the capacitor plates. Then we determined the charge in the capacitor plates as a function of time by solving that equation. Next, we found an expression for the current through the inductor by taking its derivative. And then finally, we used all of these expressions and knowledge of the max voltage and the max current to solve for the unknowns. So as a final note, I'd like to say a few words about the physical situation here. Take a look at the charge function. We'll see that it's a cosine function, and the current, however, is a sine function. These two functions are 90 degrees out of phase. And so what that means is that when one of them is 0, the other one's at a maximum or a minimum, and vice versa. So let's analyze this circuit in terms of just these functions alone. And I'll start by just saying, let's say we have charge, which is at a maximum, which means that the current should be 0. So we have a lot of charge buildup on the capacitor plates, but no charge flowing through the inductor. If there's a huge amount of charge buildup in the capacitor plates, this essentially acts as a battery, which will then start to drive a current through the inductor. And so that charge will start to be depleted on the plates, but a current will start to flow on here. After a quarter cycle later, all the charge on the capacitor plates will have been depleted, so it'll be down to 0. So this function's at 0. But now you're going to have a large current flowing through the inductor. So this function's at its max. All that current flowing through the inductor will now go to the other side of the capacitor and start to build up there. And then another quarter cycle later, you're going to have a large amount of charge build up on the capacitor in the opposite manner. So it's going to be at its minimum. But now there's no more current flowing because it's all flowed through to the capacitor plate. So now you have this at 0. So essentially, this is oscillating back and forth between one having a max and one being 0, and then one having a min, the other one being 0, etc. So you should view this LC circuit as essentially an exchange, an oscillatory exchange of energy between the energy stored on the capacitor through its charge and the energy stored in the inductor through its current. And this process will repeat endlessly. In theory, it'll repeat forever because all you have is cosines and sines, and it'll just oscillate forever. But in practice, you're going to have actually resistive elements which will cause these oscillations to die down over time. And that will be essentially taking this a step further from an LC circuit to an LRC circuit, which basically means you take this function, or this equation, you add one more term for the resistor, and then solve it again. It's a differential equation. In any case, I'll stop there for now, and if you have any comments or questions, please leave them on the link accompanying the video, and we'll see you next time.